All right, now we know all about the sum rule and the product rule. Let's move on to a couple more fundamental rules of counting. So the next one is the subtraction rule, which you may also know by the name Inclusion-Exclusion. So it's basically a little bit of an expansion of the sum rule. And what I mean by that is that it's basically the same as the sum rule, except what if the cases have overlap? So you can be in one case, or in the other case, or in both cases. Remember, this is what we were ruling out last time. So now we're saying, what if these cases overlap? Then, if you use the sum rule, you've double counted the overlap. Because if you're adding these cases plus these cases, the overlap gets added twice there, because you're adding it both times. And so there's a simple way to fix this, which is just to subtract it back off. So you double counted the overlap, so subtract it to get the correct count. So our analog for sets, remember for the sum rule, we assumed that these were disjoint. So now we're saying they're not necessarily disjoint. Then, what is the cardinality of A union B? Well, again, use the sum rule. It's the cardinality of A plus the cardinality of B minus the overlap, which is the cardinality of A intersect B. And notice that if A and B are disjoint, then we just get the regular sum rule back, because this term will disappear. So let's see an example of this. How many numbers from 1 to 1,000 are divisible by 2 or 5? So you can see that this is a situation that we were ignoring before, because these two categories, a number being divisible by 2 and a number being divisible by 5, do have overlap, namely when the number is divisible by 10. So we need to count how many are divisible by 2, how many are divisible by 5, and how many are divisible by both, which is divisible by 10. So divisible by 2 how many numbers from 1 to 1,000 are divisible by 2? Well, we know that every other one is divisible by 2, so half of them, right? So it is 1,000 over 2, which is 500. Divisible by 5, we can do basically the same thing. Every fifth number is divisible by 5, so we get 1,000 over 5, which is 200. And finally, what are the ones divisible by both? They're exactly the numbers divisible by 10, and by the same argument, the number of those is 1,000 over 10, which is 100. So the total is 500 plus 200 minus 100. which is 600. Very nice. I want to sneak in here a little trick, which is, not necessarily to do with the subtraction rule, but involves some subtraction. So let's sneak it in here. So here's a tip/trick that you can use for counting problems, is that you can work from either end. So for all of the above examples, we've counted the number of these, we've counted these objects or this set that we're interested in directly. But another idea is that you can count the complement. If you're working in a situation where this is something that's easier to count. So count the complement and subtract that from the sort of universal total. So here's another example. So say a phone number is any string of 10 digits by which I mean I'm not worrying about the many exceptions, like it can't start with 911 and keep going. So let's just say a phone number is just some string of 10 digits. How many phone numbers have at least one 9? So this trick you will often use in situations where you're asked for at least one of something. Situations like this, where it's easier to say, what is the opposite of this? The opposite of this is to have exactly none of them. So for example, if you wanted to do a direct count, you'd have to worry about how many 9s, and in which positions do they occur. Now, you don't want to worry about any of that. What you want to do instead is to count the complement. Which is to say that there are, so 10 to the 10 is total phone numbers. Okay, and then minus the number that have 0 9s in them. That's just 9 to the 10. Because this is the phone numbers made from digits 0 through 8. And that's it. So, this strategy is looking like a nightmare, whereas this strategy is just that simple. So this is a good thing to keep in mind. If you ever see something like how many things have at least one of something, you can always count the complement and then subtract that from some grand total. Okay, so those are my division rules. Sorry, subtraction rules. Little Freudian slip there, because the next one is the division rule. And the division rule is similar to the subtraction rule in the sense that it's kind of an analog to the product rule, except you overcounted something and you're dividing it out to correct the overcount. So let me say this in kind of vague language. If you overcount each object by the same amount, then just divide by that amount to get the correct count. So let's do an example where, okay, yeah, let's just do an example. So how many ways to seat 4 people at a circular table? So the point of this circular table is we're saying that it doesn't matter what orientation the people are in, it just matters who's sitting next to who. So if here's our table and we have like A, B, C, D, that's the same as having A, B, C, D. Right? You've rotated this, but the arrangement in some senses is still the same. So how many ways can we seat 4 people at a circular table like this? And for this division rule, you will often use it when there is some kind of symmetry that you would prefer to ignore until you divide it out later. So in this example, we can do this rotation, and that's some symmetry that this problem has, but it makes it a little bit tricky to count. So we start by ignoring the rotation. So we're going to break the symmetry, then count it, and then divide back out to correct. So start by what did I say? We're going to so ignore the symmetry, and let's say we count them in a line. So now that we've changed it from a circle to a line, this is more familiar, we can just use the product rule. So we have 4 pieces, which are the 4 seats. And in each seat, we can put 1 person with no repeats. So the first seat, we have 4 options. The second seat, we have 3 options. The third seat, we have 2 options. And the last seat, we only have 1 option. So this is, what is this? I guess this is 24 ways total. And now, the point is that each seating in a line, or rather, let's say it backwards, each seating in a circle corresponds to exactly 4 seatings in a line. For example, our seating that we were talking about before, A, B, C, D, we could write this in a line as A, B, C, D, but we could also think of all the rotations. So this could be B, C, D, A, or C, D, A, B, or D, A, B, C. So the point is that we've counted the number of ways to seat people in a line, and then we've said that each of those, exactly 4 of those, correspond to each of the things that we are interested in. So to find the number of things we're interested in, we just need to take this count and divide it by 4. So we find that there are 6 ways to seat 4 people at a circular table.